Hello there, science fans. Today we'll take a look at the fascinating history of atomic theory. Let us examine how our understanding of the atom has evolved over time, from the earliest philosophical musings to today's cutting-edge quantum models. The modern concept of the atom has its beginnings in ancient Greece. The prevailing view regarding the nature of matter around the beginning of the 5th century BC suggested that matter was continuous and could be divided into smaller and smaller fragments indefinitely. During this time, philosophers Leucippus and his student Democritus proposed a novel theory that called this assumption into question. They suggested that everything in the universe is composed of small, indivisible particles. These particles were dubbed Atomos, which is derived from the Greek term for uncuttable or indivisible. According to their theory, there is empty space between atoms. Atoms are indestructible and have always been and will always be in motion, and there are an endless number of atoms and types of atoms that differ in shape and size. This was a profound philosophical idea that represented a significant departure from traditional understanding of the physical world. It is important to note, however, that this was not a scientific theory in the modern sense. Leucippus and Democritus lacked experimental evidence to back up their claims. Their proposal was founded on logical and philosophical reasoning rather than empirical data or experimental validation. Moving forward in time to the 19th century, we come across a pivotal figure in the history of atomic theory. John Dalton. Dalton, an English chemist and physicist, made important contributions to our understanding of matter. He proposed that elements interact with one another using distinct, consistent weight units. To describe these units, he revived and redefined the ancient Greek term atom, giving it a new scientific meaning. Dalton's atomic theory proposed that each element was made up of a different type of atom, and that these atoms could combine in specific ratios to form compounds. This theory explained the law of conservation of mass and the law of definite proportions, two fundamental principles in chemistry. Dalton's theory was the first to have empirical support and widespread acceptance in the scientific community. Dalton's model of the atom was fairly straightforward. He imagined atoms as tiny, solid spheres, similar to tiny billiard balls. Each element was represented by a different type of atom, and the weight of these atoms varied. A hydrogen atom, for example, was lighter than an oxygen atom, reflecting their atomic weight differences. This model was revolutionary at the time because it provided a tangible representation of atoms as well as a way to distinguish between atoms of different elements. This model, however, was not entirely accurate, as we now know. Dalton's model did not take into account the subatomic particles, protons, neutrons, and electrons that we now know comprise an atom. As we near the end of the 19th century, we witness a significant breakthrough in atomic theory. J. Thomson, a British physicist, made a discovery in 1897 that would forever change our understanding of the atom. Thomson discovered the electron, a subatomic particle with a negative charge, through a series of experiments involving cathode rays. This was a significant discovery because it provided the first evidence that atoms were not indivisible as previously thought, but rather made up of smaller particles. Following this discovery, Thomson proposed a new atomic model to account for the presence of electrons. This model is also known as the plum pudding model or the chocolate chip cookie model. Thomson depicted the atom in this model as a sphere filled with a uniformly distributed positive charge. Like plums in a pudding or chocolate chips in a cookie, negatively charged electrons were embedded within this sphere. The plum pudding model's reign, however, was brief. In 1909, a physicist named Ernest Rutherford performed an experiment that would once again revolutionize our understanding of the atom. Rutherford, who was born in New Zealand and later moved to the United Kingdom, performed what is now known as the gold foil experiment. Rutherford and his colleagues fired a stream of positively charged alpha particles at a thin sheet of gold foil in this experiment. Thomson's plum pudding model predicted that the particles would pass straight through the foil. Instead, they discovered that while most particles passed through unaffected, some were deflected at large angles, and a few even bounced back. This was an unexpected result that the previous model couldn't explain. Rutherford interpreted these unexpected findings as proof of a small, dense, positively charged nucleus at the heart of the atom. He hypothesized that the atom was mostly empty space with a cloud of negatively charged electrons orbiting the central nucleus. The plum pudding model, which depicted the atom as a uniformly charged sphere, was radically altered. Following Rutherford's seminal work, the stage was set for yet another significant advance in atomic theory. This was provided by Niels Bohr, a Danish physicist who made his name in 1913. Bohr proposed a novel idea that would help us better understand the internal structure of the atom. Bohr proposed the concept of fixed energy levels or orbits within the atom. He postulated that electrons inhabit these specific orbits, each of which corresponds to a particular energy level. This was a departure from Rutherford's model, which didn't specify how the electrons orbiting the nucleus should be arranged. In addition, Bohr's model explained how electrons could move between these energy levels. He proposed that an electron could jump from one orbit to another by absorbing or emitting energy. This concept was especially significant because it explained a long-observed phenomenon, the discrete spectral lines emitted by atoms when heated or otherwise excited. These spectral lines, which were unique to each element, had been observed and catalogued for many years, but their origin was unknown. The solution was provided by Bohr's model. When electrons jump between orbits in an atom, the specific energy differences between them correspond to the specific energies of light emitted or absorbed. This explains why each element has a distinct spectral fingerprint. Finally, we have arrived at the most recent and sophisticated understanding of the atom, the quantum mechanical model. This early 20th century model is based on the principles of quantum mechanics, a branch of physics that deals with phenomena on the atomic and subatomic scales. Electrons in the quantum mechanical model are not depicted as particles moving in fixed orbits around the nucleus, as they are in Bohr's model. They are instead described as existing within a cloud-like region surrounding the nucleus, which is also known as an electron cloud or an orbital. This electron cloud represents the regions of the nucleus most likely to contain an electron. However, an electron's precise position within this cloud is not fixed or definite. It is instead described by a probability distribution. This means that the precise location of an electron at any given time is unknown. Instead, we can only discuss the likelihood of finding the electron in a specific region of the atom. The Heisenberg uncertainty principle, a fundamental concept in quantum mechanics, is directly responsible for the probabilistic nature of electron location. This principle states that it is impossible to know both the exact position and momentum of a particle, such as an electron, at the same time. While less intuitive than previous models, the quantum mechanical model of the atom provides a more accurate and comprehensive description of atomic structure. It has been incredibly successful in explaining a wide range of atomic phenomena and serves as the foundation for our modern understanding of the atom. From the ancient Greek philosophers' philosophical musings to the complex quantum mechanical model, our understanding of the atom has come a long way. Each model, while eventually being replaced, brought us one step closer to our current understanding. That brings us to the end of our journey through the evolution of atomic theory. We hope this video has helped you understand how our understanding of atoms has evolved over time. Thank you for your time.